Hello everyone. The aim of this video is to provide you with an overview of what protecting groups are, why you would want to use protecting groups when conducting an organic synthesis, and also some typical examples of protecting groups that can be used to protect hydroxyl groups, aldehydes and ketones, and in general carbonyl groups and amino groups. The video will be divided in several sections to make it easier to follow the content, and is based on chapter 7 in Smith's organic synthesis. And as a reminder, you have this chapter available through the Novel database, and the link is available on the Blackboard for the module. So the first part of the video is going to be focused in a general overview of what protecting groups are and why protecting groups are used in organic synthesis. Why to use protecting groups? Well, a protecting group is a group that will block a particular functional group, a particular reactive position, by transforming it into a different functional group that will not react. Why would you want to do that? Because very often in a synthesis, the molecule you're working with contains more than one functional group that is able to react in those conditions. And you want to selectively perform a particular reaction in one functional group while protecting all the other functional groups present in the molecule to avoid undesirable reactions. A protecting group needs to be relatively inert and stable, so it doesn't react in the reaction conditions. Once it starts protecting the functional group you're interested in preserving, it's important that it stays as part of the structure. And on the other hand, it needs to be easy enough to remove, because once the reaction has finished and you have the final product and you want to generate the original functional group that you were protecting, it is necessary that that protecting group leaves the molecule without excessive difficulties. When you use a protecting group, you tend to have two additional reactions that needs to be factored into the synthetic pathway. One is the protection reaction, the adding the protecting group to the molecule of interest to protect a particular functional group. And the second one is a deprotection, in which you liberate the original functional group that you were protecting once the reaction has taken place. What sort of groups might need protecting? Well, typically groups that have a carbonyl group might need protecting, for example, carboxylic acids, alcohol, carboxylic acid, ketones, and aldehydes. Alcohols, the hydroxyl group, often also needs protecting, and also amines tend to need protection when to avoid undesirable reactions. A carboxylic acid can often be protected by making that carboxylic acid into an ester, which is less reactive. A hydroxyl group can cause problem because that hydrogen from the hydroxyl group is mildly acidic. So it might need protecting by converting it into an ether or an acetal or even an ester, which will remove that acidic hydrogen, and will avoid that acid-base reactions. A carbonyl group in aldehydes and ketones can also often needs to be protected, and you can do that by converting it into an acetal or a ketal, or a thioacetal or a thioketal, or sometimes by converting it into a hydrazone. Amines can also give problems and undesirable reactions because they have a very rich acid-base chemistry. So they can behave as a base and be involved in acid-base reactions, but they can also that hydrogen can also be mildly acidic depending on the pH conditions. And then the protecting group, the role of the protecting group would be to protect that acidic hydrogen to avoid reaction. And what can it be done with amines? And we will discuss it later in the video. Well, they can be converted into ammonium salts. They can be converted into amides or sulfone amides as typical examples. This is an example of a reaction in which you might need to protect a hydroxyl group. So we've got this product, this is what we're aiming for. And if you look at this as a retrosynthesis, so when you look at this compound, it has two hydroxyl groups and a carbon chain. So one way of introducing this carbon chain here would be by using a Grignard reagent. So using a Grignard reagent in an aldehyde to form the final product. And the idea is that your Grignard reagent only reacts with the carbonyl group from the aldehyde. However, the presence of this hydroxyl group might be a problem, because you could form an alkoxide with the Grignard reagent, which it would change the solubility of the product. And a way to avoid the Grignard reagent forming an alkoxide with this hydroxyl ion would be to protect that hydroxyl ion. So the Grignard reagent has only one place in the molecule it can react. That's the aldehyde, the carbonyl group. So, for example, a way to protect that hydroxyl group would be to make it into an ester. The ester does not react with the Grignard reagent. You have the reaction between the Grignard reagent and the aldehyde. You form the final compound, but with this alcohol still in ester form, and then by acidification you break the ester and you liberate the hydroxyl group. This is another example of a reaction that involves the protection of a hydroxyl group. And in this case, the protective group is this tetrahydropyranyl group. So in the first instance, you have a diol, a 1,3-propane diol, and you make it react with dihydropyran, which is this compound here. And this hydroxyl group now becomes protected. Then you do a series of reactions on this hydroxyl group, and then finally, when the almost final molecule is achieved, this would be compound 10, you use acidic medium and methanol to remove that THP protection and liberate the original hydroxyl group that you have in the molecule. An interesting article in which discusses the use of THP as a protective group in a biochemical context when working with peptide chemistry is the one mentioned in the slides by Sharma et al. And it's an open access paper, and you have the link in the resources for this week on Blackboard. This is an example of the use of a protecting group to protect two functional groups at the same time, in this case two hydroxyl groups. And it involves the formation of a ketal, and this is a ketal. So as you can see, the formation of the ketal means that those two hydroxyl groups are protected. There is a reaction on the alkene group in double bond in the structure. Once this methyl and this hydroxyl group have been introduced, you can break the ketal and liberate the compound by using hydrochloric acid as catalyst and distilling. And interestingly, as you see, this protection also creates a change in the general structure of the compound, and that is because this 5-member ring is more stable than this original 7-member ring. So the compound is a new structure, a new cycle is formed. This is an example of a reaction in which you have several functional groups, but in your case you have a hydroxyl group and an amino group, and the objective of the protection is to protect the amine. So the reaction can happen in the hydroxyl group to form, or in this case, an aldehyde, and the amino group be protected. So the way it was achieved in this case was by converting the amine into an amide, an acetamide. So there is an oxidation of the hydroxyl group with something called the Collins oxidation, which is a chromium reagent with pyridine and dichloromethane. The formation of a carbonyl group, an aldehyde, and in this case you've got the amide still protected, that then can be liberated, for example, by hydrolysis with in acid medium, for example.